Welcome to another podcast. In this episode, we're going to be taking a look at the repeated root case for the first time. We've sort of run into problems with this case previously because if we're looking at, say, this differential equation, we've got, let's do it in terms of t here, p of t y prime plus q of t y equal to 0. Then if this equation has the following characteristic equation, so let's suppose that its characteristic equation ends up being this, then the idea is there are two real roots. And so we know from previous experience that one of the solutions will be one of the roots, but what will the second solution be? That second solution can't be the same as the first, or else they'd be linearly dependent, and we know we wouldn't be able to solve the IVP in that case. So all I can do is go from the information I'm given, and if I know that r plus a squared equals 0 is the form of the characteristic equation, then if I pull out terms, so if I go ahead and FOIL this out, then this is what the characteristic equation must look like, which means the equation it comes from must look like this. So this is the only type of differential equation, at least constant coefficient equation, that will give repeated real roots. And so I know what my first solution is. How can I find my second solution? Well, if you look at this, this gives me p is equal to 2a and q is equal to a squared if we're in this case. So I want to apply the reduction of order method. Now we talked about this in a previous video, but this method says that if you have a solution y1, then a second solution is given to you by v times y1, where v is the integral of 1 over y1 squared e to the integral p of t dt and dt. So we're going to apply that in this case. We know what our y1 is. It's e to the negative at. So when I square that, I get e to the negative 2at. So I've got 1 over e to the negative 2at in the denominator. And then this is e to the integral. P is 2a, so 2a dt dt. All right, if we do the inner integral, the integral of minus 2a with respect to t is e to the minus 2at. And nice enough to see that we have this cancellation occur, leaving us with just the integral of dt, which is t. So according to the reduction of order method, the v that we need is the function t, which means our second solution should be t times y1, or t e to the negative at. So there's my second fundamental solution. If I go back over here to where we started, we now know that if you end up in the repeated root case, if you've got a root that's repeated twice, then the first part of the fundamental set is just e raised to that root like you would do for any of the other cases. Then the second solution you have to multiply by t. Now the question is, given what we have here, do we know that these are a fundamental set? Do we know that these form a fundamental set? Well, we know because of the way we derive the reduction of order method, we know this thing is a solution. We know e to the negative at is a solution. Do we know that they are linearly independent? Remember, we have to check the Wronskian. So I'm going to do that now. I'm going to check the Wronskian of e to the minus at, t e to the minus at. And this is equal to this determinant. So we've got e to the negative at, t e to the negative at, minus a e to the negative at. I've got to take the derivative of each of these. And this one's going to involve product rule. And if you do product rule correctly in this, you're going to get 1 minus AT e to the negative AT. So I've got to look at that determinant. And I'll do that over here. Let me create a little space here. So over here on this side, if I look at that determinant, remember it's the cross diagonals. So it's 1 minus AT e to the negative 2AT. If you multiply these two together, remember you add the exponents. And then it's minus that off diagonal. That off diagonal is going to be minus AT e to the negative 2AT. And so that's equal to 1 minus AT plus AT e to the negative 2AT, which is just going to give us a 1. So this is going to get e to the negative 2AT. So this is the Wronskian of those two. And the question is that ever 0? And we should know by now that it's not. This is never equal to 0, and once again, this is for any t. So this implies that y1 equal e to the negative AT and y2 equal t e to the negative AT form a fundamental set of solutions, and this is the fundamental set of solutions that corresponds to this equation. It's the repeated root equation case. All right, we're going to look at a numeric example in the next video, but from now on we can just assume that we know the fundamental set of solutions for the repeated case is the exponential and then the exponential times the dependent variable, either t or x or whatever the problem's written in terms of. Okay, thank you for watching.